Hello, everyone, and welcome to today's lecture. Today, we're going to be talking about sparse matrix computations. But before, and this lecture is going to be in two parts. So today we're going to do part one, next time we'll do part two. But before we do that, let's go back and review what we covered in our last lecture. So our last lecture was about sorting, and we looked at three different ways that we can do sorting on GPUs. Of course, there are many other ways, but we looked at three different ways just kind of as to get an intuition for what sorting entails on GPUs. So the first example of sorting we looked at is odd-even sort. And odd-even sort is one of those O of n squared sorting algorithms. So it's similar to bubble sort, not exactly the same, but similar to bubble sort in the idea that you keep iterating, and then in every iteration, you sort adjacent pairs of elements, and you keep doing iterating over and over and over again until the list stops changing, in which case you know that the list is sorted. Now with odd even sort, the idea is that if you want to be able to sort pairs of elements in parallel, you never want to have the same element being sorted by different threads. So what we do is we have one thread for every pair of elements that sorts that pair, and then we alternate between odd pairs and even pairs, and we keep alternating until the last list stops changing. Okay. Now, of course, this is a very easy sort to implement, very simple, but the problem is it's O of n squared, which is not good for very large lists. So we also looked at parallel merge sort, and parallel merge sort was easy to talk about because in the previous lecture we had already talked about how to do a parallel merge. So if we know how to do a parallel merge, the parallel merge sort is very easy, right? You start by sorting different small subarrays of the list or sublists of the list, and then you start merging pairs of sublists in parallel. And every time you merge fewer but larger sublists until you get the final list in fully sorted order. So in the early iterations, you get parallelism because you have many merges that you can do in parallel, and you get a little bit of parallelism from within the merges. And then in later iterations, you're going to get a lot of parallelism from within the merges and little parallelism across merges because you have half the number of merges to do every iteration. So that's how parallel merge sort works. And then we looked at radix sort, and we said that the main challenge of parallelizing radix sort is how to parallelize one iteration of radix sort where we take a bunch of keys and we partition them into different buckets based on the digit of interest in each iteration. And we said that this is very similar to the filter pattern that we looked at before, but it's a generalization of the filter pattern. In the filter pattern, we were taking elements that meet one criteria and filtering it and throwing everything else out. In this partition pattern, it's a generalization because we are taking the elements that meet a criteria into one bucket and the elements that don't into another bucket. And then if we have more than two buckets, we're basically taking elements into different buckets. And we said that we can do this by basically formulating the whole partition operation as an exclusive scan. And we did that, and then based on the exclusive scan, every thread can identify where its element has to go to in the final output list, and then it can write that element into the output list. Now we said that one of the main things that is inefficient about this computation is that once every thread has identified where to write its output element and wants to go and write it, we have a lot of uncoalesced accesses. You can see over here, adjacent threads are going to be writing adjacent elements to different locations in global memory, and this results in poor coalescing behavior. So what we said we can do instead is we can do packing, where instead of writing out the elements in a scattered way to the global memory, we pack the elements that are going out to locations adjacent to each other in the shared memory. So every thread we will partition the elements inside of a block within the shared memory into two contiguous buckets. And then each of these buckets will be written out from the shared memory to the global memory in a coalesced way. And this improves the utilization of the memory bandwidth when we are doing these stores. We then said that we can reduce the number of iterations in radix sort by using a larger radix value. But the drawback of using a larger radix value is that now we're going to have more of these buckets, and when we have more buckets, that means we are writing out to more distinct memory locations in global memory when we do the final store. And then the drawback of that is that we will have fewer coalescing opportunities because now instead of having a few large buckets in the shared memory that we need to write to global memory, we have more smaller buckets that we need to write from the shared memory to the global memory. And the way that we can overcome that is by applying thread coarsening, where we give every thread block more elements to process than the number of threads that it has. And by giving it more elements, we're going to go back to having larger buckets. And then now when we write these buckets from the shared memory to the global memory, we will have more opportunities for coalescing. Okay, so this is what we covered last time. Any questions about what we covered last time? All clear? Okay, so then today we are going to look at sparse matrix computation. Okay, so what is a sparse matrix? Who knows what a sparse matrix is? What do I mean by sparse matrix? Right, a sparse matrix is a matrix that has very few non-zero entries, right? The matrix is going to have entries, but when a lot of these entries are zero, right, we call this a sparse matrix, exactly. So a dense matrix is a matrix where the majority of the elements in that matrix are not zero. A sparse matrix is a matrix where the majority of elements in the matrix are zero, and we have a few elements that are not zero. Okay, and it turns out that for a lot of real world problems, many of these systems that we use matrices to represent are sparse. Okay, usually when we have matrices, these matrices could represent things like systems of linear equations, right? A matrix is sometimes a representation of a system of linear equations. Now, when we have a system of linear equations, it could, if I have 1,000 equations with 1,000 unknowns, right? There are many cases where not every equation is going to have every single unknown in the system represented. Different equations will have different unknowns represented, and some unknowns are not going to appear in that equation. And that's where the sparsity comes from. Okay? And that's why many real-world systems are sparse. So why is sparse? Why is it useful to think about the sparsity of a matrix? Why is knowing, how does knowing that certain elements are zero help us in the processing of this matrix?
Less computation, maybe, and if they are zero, so that we don't make anything on them.
Right. So you're both absolutely right. So somebody in person answered, somebody online answered. You gave the same answer, which is if I know that an element is zero, I don't need to compute with it because I know that multiplying by zero gives me a zero, which doesn't affect the ultimate result. And also, if I know that an element is zero, why bother loading that element from memory? Okay, I can have some kind of representation where I compress my matrix, remove the zeros, and that way I don't have to spend memory bandwidth loading these zeros from memory. So sparse matrices gives us a lot of opportunities for optimization. We don't need to allocate space for the zeros in memory. This saves memory capacity. We don't need to load those zeros from memory. This saves memory bandwidth. And also, we don't need to compute with these zeros. So this saves us computation time. Is this clear? Yeah, any questions? Okay, everybody sees the difference between saving memory capacity and saving memory bandwidth, right? It's one thing to save how much memory we use, and it's another thing to save how much memory we transfer from the memory to the CPU. These are two different things. Okay, great. So now we know that sparse matrices, it is useful for us to take sparsity into consideration when we are representing a matrix. So how do I take sparsity into consideration? I need to have some kind of storage format where I represent the matrix in a compressed way that helps me ignore the zeros when I'm accessing and when I'm computing. And that's why we have a lot of sparse matrices, sparse matrix storage formats. So there are many storage formats that are used for storing sparse matrices. Different formats have different strengths and weaknesses. So what we're going to do today and next lecture is we're going to look at these different formats and look at how the formats impact the way that we will write our kernels to compute with the sparse matrix. Okay? Okay, So the formats we're going to look at are one, the coordinate format, which we abbreviate as COO, the compressed sparse row format, which we abbreviate as CSR, the LPAC format, which we abbreviate as ELL, the jagged diagonal storage format, which we abbreviate as JDS, and there are other formats, but for this course, we're going to focus on these formats. We're going to also look at a variant of CSR, which is CSC, compressed sparse column. So today we're going to look at COO, CSR, and also CSC, the compressed sparse column. And next time we will look at ELL and JDS. Is this clear? Okay. So what considerations go into the design of these formats? Well, why are there different formats, and what do we worry about when we design these different formats? Well, there are several considerations that go into when we're designing a format. The first one is space efficiency. How much memory does this format take to represent the matrix, right? Some formats are going to be more space efficient than others. They're going to use up less memory. They're going to have a better compression ratio than others, right? But other formats might be less space efficient, but they may enable us to do certain things in a better way. The other one is the modifiability of a matrix. How easy is it to add elements to the matrix, to remove elements from the matrix, to modify elements in the matrix, okay? Now, in many computations, we don't care about adding or removing elements. But in some computations, we might. And that's why some formats could be, better at adding and removing elements, but maybe worse at other things. Is that clear? Okay. Another one is the accessibility that the storage format provides. What kind of access does the format make easy to do, and what does it make difficult to do? Some formats might make it easy to go through elements in the same row, but hard to go through elements in the same column. Some formats might make it easy to go through elements in the same column, but hard to go elements in the same row. Some formats might make it easy to, if I grab a random element in the matrix, find out which row and column that element belongs to. In some formats, that might be difficult. Okay, so different formats will give us different kinds of accessibility into the matrix. The other one is the memory access pattern. So does this format help me access when I'm doing parallel processing on the GPU, does this format help me access the matrix in a friendly access pattern? In particular, does it enable coalesced memory accesses when I access the matrix? And another one is load balance. And what we mean by load balance is when I am using this format to perform a computation, does the format make it easy for me to have low control divergence or high control divergence? And even across warps and across blocks, does the format make it easy for me to have a balance of work across warps and blocks, or is the work very imbalanced? But mostly, this is most critical when it comes to control divergence within a warp. Does the format make it easy to have threads in the same warp do a similar amount of work? Okay. So these are the considerations that we will review, and every format I introduce, we're going to go back to these 5 considerations. Okay, maybe write them down somewhere so that we can revisit them. Okay, so we will go through these 5 considerations every time, and we will assess, right, how this format does on each of these considerations. Clear? Okay. Now, the best format usually also depends on the type of computation that we're performing. Different computations would prefer different formats. So what we're going to do in this lecture, we're going to focus on like the hello world for sparse matrix computations, which is SPMV. Like I said, the choice of the format depends on the computation. We will be looking at SPMV, which stands for sparse matrix vector multiplication. And we will be using SPMV as a case study for today's lecture and next time's lecture. So what does SPMV do? Like the name says, sparse matrix vector multiplication. It takes a sparse matrix, multiplies it by a dense vector to give us another dense vector. Okay. Now this isn't the only sparse matrix computation we do. It's a very common one, sparse matrix vector multiplication. But we might want to do things like sparse matrix, sparse vector multiplication. We might want to do sparse matrix multiplication. We might want to do sparse matrix, dense matrix multiplication. We might want to do in your project, for example, a sparse matrix lower triangular solver. Okay, so there are different kinds of computations that we will do. You can do with sparse matrices, and for different computations, different formats will be better. Okay, so what we will be looking at in this lecture and next time is sparse matrix vector multiplication. Everyone understands what SPMV does. Do I need to explain it? You multiply the dense sparse matrix by the dense vector, exactly. Okay, so every output vector element is going to be the corresponding sparse row multiplied by the corresponding dense vector. Okay, we'll see. So somebody asked, how do not access visual? We'll see. The formats are going to help us do that. Yeah, so here ideally, if you want to compute this, the first output element, we just want to go over the 3 non-zero elements, find the corresponding 3 non-zero elements in the dense vector, and then just do a dot product of those to get the output element. I don't want to load and multiply with these 0 elements. I mean, here we're talking logically about the computation, but we're going to see how we're going to physically implement this depending on the format. Okay? All right. So let's start with the first format, which is the coordinate format. And then to explain to you the coordinate format, I'm going to use this example matrix throughout the lecture. Okay, this is an example of sparse matrix. It's not very sparse because it's small, right? Almost half the elements are there. Usually sparse matrices that we deal with are very sparse. We're talking about 10% of the elements are non-zero, or 1% of the elements are non-zero, or sometimes even 0.1% of the elements could be non-zero, right? Or even less, right? The matrices can be very sparse, and usually for these formats to be effective, the matrix should be very sparse. If a matrix is 50% sparse, a lot of times it's just better to treat it as a dense matrix than to treat it as a sparse matrix, okay? So here in this example, the matrix is around 50% sparse, but just because I need a small example to fit on the slide, but keep in mind that if the matrix was 50% sparse, you wouldn't be doing some of the things we're going to talk about today, and you'll see why. Okay, but we usually these techniques are usually targeted at matrices that are much more sparse than this. Okay, so what does the coordinate format do? Well, the coordinate format simply stores every non-zero in the matrix along with its row index and its column index. Okay, so here what I will do is I will take these non-zeros and I will store them in an array. And then I will have 2 other arrays where at the same location, they will store the row index and the column index of the elements. Okay, so here in the first, this first element indicates that at row 0, column 0, I have a 1. At row 0 and column 1, I have a 7. At row 1, column 0, I have a 5, etc. And these elements don't necessarily need to be sorted. Okay, so here I happen to put them sorted, and usually they are sorted, but they don't necessarily need to be sorted. I can randomly shuffle the elements in the COO. I can randomly shuffle the order of the elements in the COO format, and it's still supposed to work. Okay, I don't lose information by shuffling the order of the elements. Is this clear? Okay. Okay, great. So now we understand how the COO format works. Now the question is, how can I use the COO format to perform SPMV in parallel? Okay, so what I would like to do is I would like to, in parallel, multiply this matrix with this dense vector to get a dense vector, okay, using the COO format. Any ideas of how we can do this? Wait, one at a time? Yes? Okay, so somebody is saying that here for 7, I can look up that 7 is at row 0 and column 1. So using this information, I can find the input value at index 1 in the input vector, which corresponds to the column index. I can multiply that value with 7, and then I can use that value to update the output element at the row index, which is 0. Right, that's exactly what we do. That's how we do for one element. And if I want to do it in parallel for a lot of elements, what would I do? What would I assign threads to? Right, every thread can take one non-zero element, right, and can do what we just said. So here, the parallelization approach is I assign a thread to every non-zero element in the matrix, and that thread can look up the column index and the row index, load the element from the input vector at the column index, multiply it by the value, and then update the value in the output vector at the row index. So somebody observed that when we do this, we have a race condition because multiple threads here, these two threads are both going to want to update this value. So how can we get over the race condition? We can use atomic operations. Yes, 1 and 7. So the thread assigned to 7 and thread assigned to 2 will both load from the same input value. I don't have a problem with loading. The problem is when the different threads are going to write to the same output value. And here, to overcome this race condition, what we need to do is we need to use atomic operations. Is this clear? Okay, let's go and implement this and see what the implementation looks like. I'm going to switch to my code. Okay. So here I've started us off with a sparse matrix kernel that takes as input a COO matrix. Just to show you what the COO matrix looks like, it looks like this. It has a field that tells me the number of rows in the matrix, a field that tells me the number of columns in the matrix, a field that tells me the number of non-zeros in the matrix, and then an array for the row indices, an array for the column indices, and array for the values. Okay, not surprising. Any questions about the representation? Okay, so using this matrix, what I would like to do is I would like to go and implement this SPMV kernel. I've already kind of launched this kernel, and the number of threads I gave to the kernel is equal to the number of non-zeros that we have inside of the matrix. Okay, which is the length of the values array, the row array, the column array. Exactly. So here, what we're going to do is we're going to start by assigning every thread to a non-zero. I'm going to use I to indicate the index of the non-zero. So for instance, I equals block index.x times blockdim.x plus thread index.x. I need to do a boundary check because the number of non-zeros may not be divisible by the block size. So I can write if I is less than COO matrix dot num non-zeros. Okay, and now every thread is going to have to go and load the row index, the column index, and the value of the non-zero that it is responsible for. Yes, somebody has a question. Yeah, somebody's asking how does it know that yes. So somebody's asking how do we know that these elements, where to find them? They're already given to the kernel in this format. So here the COO matrix struct that I just explained to you, that was there was a pre-processing that happened before, and that pre-processing ensured that this format is already prepared in this. Okay. All right, great. So now what we need to do is every thread needs to go and load the row index, the column index, and the non-zero value of its elements. So that's easy. We're doing unsigned int row is equal to COO matrix dot row indices of I. Right? Is that clear? Unsigned int column is equal to the COO matrix dot the column indices of I, and then we're going to have float value is equal to the COO matrix dot values of I. So now what I did is I went to the matrix and every thread loaded its row index, its column index, and its value. Question? Huh? Do we need the row index? Somebody is asking, do we need the row index? Where do we need the row index here? So the column index tells me which element in the input vector I need to load from. The row index tells me which element in the output vector I need to update. So that's why we need the row index. You're right. Okay. So now that I've got these elements, what I need to do is I need to go and load the corresponding input value at the row index. I can do that. I can write float inval is equal to invector of column. Okay. Did I make a mistake? No? Okay, somebody mumbled something. Okay. Okay, so I load the input value. Now what I want to do is I want to multiply the value in the matrix with the input values. I want to multiply the value in the matrix with the corresponding input value that I loaded. And I want to go and I want to atomically update the output value. Okay, so to atomically update the output value, I need to get an atomic reference to that output value, right? What is that output value? It's out vector of row. Okay, so let me create an atomic reference for that. So I can do CUDA atomic ref. The type is a float, and the scope. What's the scope? Device, right? Because here any thread in the grid could be updating any output value. So I need to make sure it's atomic across the entire device. I do CUDA thread scope device, and let me call this outref, and it's an atomic reference to the out vector of row. Okay, so now I got an atomic reference to the output element in the output vector. Question? I made a typo as usual. Oh, there we go. Thanks. Thank you for catching my typos. So, by the way, that's why pair programming is useful. When you're programming in pair, you catch each other's typos. Okay, here I have more than pair programming. I have group programming, which is great. So CUDA atomic ref, we float CUDA thread scope device out ref, exactly. Now we're going to do out underscore ref dot fetch and add. What do I want to add? What do I want to add to the output element? The multiplication of the matrix element and the value loaded from the input vector. So here I'm going to multiply val times inval. Okay, and what are the semantics? The order semantics? Is it relaxed, release, acquire? It's relaxed, exactly, right? I'm not setting a flag to release another block or waiting to acquire something from some other block. So it's going to be CUDA memory order relax. Okay, so this is our SPMV implementation using the COO format. Okay, now let me compile and run. Although I tried earlier today, the GPU nodes were down. Well, at least it compiles correctly. Okay, looks like maybe they got them back up. Okay, so we can wait for it to kind of finish running. Okay, but now having seen the COO implementation, let's go back and revisit these 5 design considerations that we talked about. Okay, it seems like it'll run for a while, so we'll come back to it. Seems the system is busy today. Okay, so let's go back and revisit these 5 design considerations. You can remind me what the design considerations were. So space efficiency. First of all, how does the COO format do on space efficiency? If I have an n by n matrix with m non-zeros, so let me not use n and m because it's hard to hear the difference. If I have an n by n matrix with z non-zeros, right? What is the size of the representation going to be? 3z. Right? I have 3 arrays. Each array is going to have z elements. So here the size is going to be 3z. Okay? Is 3z compared to n squared? Is 3z a good compression factor? It could be, but you will see later on that we can do even better than 3z. So compared, we haven't seen other formats in the future, but compared to the formats that we're going to see, COO doesn't win on space efficiency. There are formats that are more space efficient than COO. Okay? All right, what's the next factor? So modifiability. Okay? Is it easy to add and remove elements to the COO matrix? Yeah, it's very easy, right? I just append to these arrays. If I want to add an element, I can very easily add an element by appending to these arrays. If I want to remove an element, that's a little more difficult, right? Because It might create holes inside of my representation, but I can deal with that by having tombstone values. And as long as I don't remove too many elements, having a few tombstone values in the array is not too big of a deal. Okay, but in particular, adding elements is very easy, and that's why a lot of times when we are reading a matrix from a file, we tend to like to use the COO format. Why? Because we can read from a file and start filling, or if not necessarily from a file, if we're constructing the matrix dynamically in some other function. So I have another function that's building this matrix. We usually use the COO format to generate the matrix because it's easy to keep adding new elements. And later on, once we've generated the matrix using COO, we tend to convert it to some other format. So COO does great on modifiability. Okay, what was the next consideration? Accessibility. So what kinds of accesses does the COO matrix make it? Does the COO representation make easy, and what kind of accesses does the COO matrix make hard? Right. So given the row index of an element, or given the row index of an element, is it easy to find the element, and the column index, is easy to find it, or is not easy to find it? So here, given the row and the column index, it's not easy to find an element. So given a row index, is it easy to find all the elements in that row? Somebody's saying if it is sorted, even if it is sorted, I have to do a search to find them. So given a row index, it's not easy to find all the elements in that row. Given a column index, it's not easy to find all the elements in that column. But what was easy to do, given a non-zero element, it's easy for me to find what row and what column that non-zero belongs to. Is this clear? Okay. So somebody's saying walking through elements in the same row. No, walking through elements in the same row is not easy because, like I said, the COO format does not necessarily need to be sorted. It can have an arbitrary sorting order. Okay. So the easy thing about COO is, given a non-zero element, I can easily find what row and column it belongs to. However, all the other things, given a row, given a column, go find the elements in these row and column. All that is hard to do with COO. So somebody's saying, if I have a non-zero value, do I need to iterate? No. If I give you the index of a non-zero value, so I tell you if I give you the index of an arbitrary non-zero value, and I tell you find me what row and column it's in, I don't need to do any iteration. I simply take the same index into these other two arrays, and I find the corresponding row and column index. Okay. Okay, great. So now we understand the pros and cons of the COO. Or sorry, that was the third one. So the fourth one. So memory accesses. Okay. Does the COO format for when we're doing SPMV? So when we talk about memory accesses, that's related to the specific computation that we're doing. So for SPMV, does the COO format enable coalesced memory accesses? Well, here I have three different structures that I'm accessing. So let's talk about each one separately. For the sparse matrix, are my accesses to the sparse matrix coalesced? Yes, they are. Right? The accesses to the sparse matrix are coalesced. Adjacent threads are going to be accessing adjacent elements in my row, column, and values array. So accesses to the sparse matrix are coalesced. That's a positive thing about COO. For the input vector, are my accesses coalesced? No. So assuming that if we don't assume any particular sorting of the elements, the accesses to the elements are not going to be coalesced. If the elements are sorted by row order, then the accesses to the input vector could be coalesced. But in principle, if they're not, right, which is allowed, they're not necessarily coalesced. Are the accesses? How about the accesses to the output vector? They're not coalesced, and not only are they not coalesced, they are atomic operations, which is even more expensive, right? So accesses to the output vector are horrible. Accesses to the input vector are okay. Accesses to the input matrix, which is the biggest, right, are excellent. Okay, so that's how coalescing plays out for COO. What was our last consideration? Load balancing. So for load balancing, how does the COO format do on load balancing? Do adjacent threads do similar amounts of work, or do I have control divergence? Similar amount of work. All the threads are doing the same amount of work. Each thread takes it on zero, right? And there's no, if you look at the code, there's no control divergence happening. Okay? So somebody's asking, will we have a control divergence when it comes to this operation? It depends on the format. Some formats are good at mitigating control divergence. Some formats are not. For COO, we don't have a control divergence problem. Okay? So this is the code that we wrote. And to recap, the advantages of COO, it's easy to add new elements to the matrix. That's why we commonly use it when we are generating a matrix. Given a non-zero, it's easy to find the row and the column. And then for the memory accesses to the input matrix are coalesced, and we don't have control divergence. These are the advantages. For the disadvantages, given a row or a column, it's hard to find the non-zeros in that row or column. We have to do a linear search. The memory accesses to the output vector require atomic operations, and the memory accesses to the input vector may or may not be coalesced. Okay? All right. So now that we've seen the COO, what do you think is going to be the most expensive part of the COO format? What's gonna be our performance bottleneck for COO? What's gonna hurt performance the most? The atomic operations, exactly. What's gonna hurt performance the most is these atomic operations. How do you think? How can we get rid of these atomic operations? So somebody said privatization. The problem with privatization is the input vector is very large. So having a private input vector for each block can be kind of quite expensive. Okay, and also there's kind of I mean, if the COO matrix is sorted, then chances that threads in the same block access the same input matrix are high. But if the COO format wasn't sorted, then the chances that threads in the same block are going to all access the same value in the private copy are low, which means that we don't really benefit too much from privatization. So somebody is asking, will a private copy be the input or the output? Usually it's the output. When we talk about privatization, we're privatizing the output. Oh, sorry, I must have misspoke. Yeah. Do we benefit from putting the input in shared memory in this case? I don't have too much reuse of the input, right? I don't have too much reuse of the input, and the reuse that I do have is very arbitrary. I don't have control over the reuse of the input, so we don't really benefit from having the input in shared memory. Let's go back to the atomic operation. Somebody mentioned warp level primitives, but the atomic operations by adjacent threads are not necessarily going to the same output element. Usually the coalesced atomics, which the compiler will do anyways, is applicable when all the threads are atomically updating the same counter, but that's not the case here. So what can we do to get rid of the atomic operations, not just optimize them? Why do I have atomic operations in the first place? Because I have different threads are writing to the same output element. So if I don't want to have atomic operations, what should I do? Right, exactly. If I don't want to have atomic operations at all, what I can do is I can have only one thread responsible for each output element. No other thread can access that output element, and therefore I get rid of the race condition, and I don't have to use atomic operations. But if one thread is going to be responsible for each output element, that means what will that thread need to do? It has to go and process all the non-zeros of the same row. Okay, and to do that, what kind of accessibility into the matrix do I need? I need to be able, given a row index, go and find all the non-zeros in that row. Does COO give me this accessibility? No. So to be able to do this, I will need a different format that allows me to, given a row index, go and find all the non-zeros in that row. Why not just have a sorted version? So somebody's asking, why not just have a sorted version of COO? Because even if you have a sorted version of COO, how do you find where the non-zeros of that particular row start? You would have to do a binary search, right? But binary search is expensive, right? This is an O of n operation. I don't want to add a log n factor to it. Okay. All right. So So what we want to do is we want to somehow group the non-zeros by row to be able to access them. And this is what the compressed sparse row format does. Okay. So for the compressed sparse row format, if I have the same matrix right here, what I want to do is I want to store the non-zeros in the same row adjacent to each other, and then have an index that tells me where the non-zeros of a particular row are located in my array. Okay, and that's going to look like this. I'm going to store the non-zeros in the same row adjacently. So here, I'm going to put non-zeros in the same row right next to each other. Okay, so the elements in the first row, 1, 7, they're over here. The elements in the next row, 5, 3, 9, they're over here, etc. For each one of these, I'm going to represent, also have another array that tells me the column index of this value. Okay, but instead of having a row index array, I'm going to have what we call a row pointers array. They're not pointers, they're offsets into these other two arrays. But basically, the row pointers array is going to tell me the starting index of the non-zeros of each row. So here, this tells me that for the first row, the non-zeros start at index 0. For the second row, the non-zeros start at index 2. For the third row, the non-zeros start at index 5. For the fourth row, the non-zeros start at index 7. And here, I'm going to have a fifth element, even though the row only has, the matrix only has 4 rows, I'm going to have a fifth element. And the fifth element is going to tell me the total number of non-zeros in the matrix, because then this tells me where the last row ends. And now, if I want to go and find the non-zeros in a particular row, I know where they start. I look at the row pointers for that row, and I know where they end because I look at the row pointers for the next row. And if I'm the last row, I look at this last element over here helps me find where that last row ends. Is this clear? So somebody asks if a row is empty, it doesn't have any elements, then I will put. So let's say here row 3, this row, this third row was empty. Then over here I will have 5, and then over here I will also have 5. And that way I know we start at 5, we end at 5. So when I iterate from 5 to 5, I won't do anything. So somebody's asking if a row was empty, wouldn't it just not be included in the matrix? It depends on where the matrix is coming from, right? So if it's like a system of linear equations, then maybe the row would not be included because that just means I don't have an equation there. But if it's coming from a different kind of system where the row indices and the column indices have particular physical meanings that I need to retain, then you could end up in a situation where you have a row that is empty. Okay, you'll see later on that sparse matrices are also used to represent adjacent lists of graphs, for example. And if I have a vertex that doesn't have any edges, it's an isolated vertex, then the row is going to be empty, okay, for that vertex. That's an example for you could have an empty row, but you still need to have that row. Somebody's asking why we need the 8. The reason we need the 8 is we want to know where the last row ends. Yes, yes. So you'll see when we're going to write our code, we're going to iterate from row pointers of the row to row pointers of the row plus 1. So this just helps us that when we iterate for the last row, we can go get the size, the total. This is the total number of non-zeros directly. Yeah. Okay. Question? Okay, so that's a very good question. Somebody's asking why don't we take into account the pre-processing that happens? That's a very good question. So each one of these matrices requires certain pre-processing to get, right? And that pre-processing, different formats could have a different pre-processing overhead. So a lot of times when we use these sparse matrices, the pre-processing is something you do once, but then you'll end up using the matrix over and over. So a lot of these sparse matrices could be part of iterative solvers, for example. An iterative solver might do this matrix vector multiplication 1,000 times. So when you're doing the SPMV 1,000 times, the pre-processing overhead is very small compared to the time that you actually spend doing the computation. So that's why a lot of times people don't reason about it. But however, in certain solvers, you might end up doing the sparse matrix vector multiplication maybe 6 or 7 times. So in this case, the pre-processing overhead could be significant compared to the computation, and you would take into the pre-processing overhead into consideration and try to favor a format that doesn't have a high pre-processing overhead. Okay, so there's a trade-off, and the pre-processing overhead is certainly part of that trade-off, but I didn't ignore it. I'm kind of ignoring it in this lecture, but I'm glad that you did mention it. It is important. Okay, other questions? Okay, so now that we know how CSR works, let's look at how we can do SPMV using CSR. So, right, the whole premise is, how do we do the parallelization in this case? That was our whole premise, right? Right, we assign a thread to every output element, and that thread is going to go and loop over the elements in the corresponding input row. Okay, so here I'm going to assign a thread to every element. The thread is going to start at the first non-zero element in that row, right? So if you look at what's happening when I'm accessing these input arrays, every thread is going to start at the first non-zero element in that row, and then the threads will load the corresponding input value, multiply, and they'll accumulate to some accumulator, and then they'll iterate. So then every thread moves on to the second non-zero element in each row. Here, this thread is done because the row only has one non-zero element. And here we can see how every thread is assigned to the second non-zero element in each row. And then this thread is just inactive because we're done processing the non-zero elements. And then we keep iterating again. So here, these two threads now drop out because the row only has two non-zero elements. But then this thread is still active because this row has three non-zero elements. So here, this thread is active, the others are inactive. And we keep iterating until we are done. Okay, question? Right, so somebody pointed out that we've traded off memory coalescing and also load balancing. Right, exactly. So here, we are able to get rid of the atomic operation, but on the other hand, we're paying the price in memory coalescing, and we're paying the price in load imbalance. You're absolutely right. Okay, so we'll come back and revisit these considerations. But first, let's go and implement the CSR. So I'm going to talk about these considerations, the advantages, disadvantages, but let's go and implement it just to get a feel for how the format works. Okay, so I'm going to switch to the code. You have bad luck today with the system. I think the nodes were down for kind of all night, and a lot of jobs queued up. So unfortunately, it looks like we're not going to be able to. Okay, so now here I have a kernel that is in CSR form that for the CSR format. Here I'm passing a CSR matrix instead of a COO matrix. Let me show you the representation of the CSR matrix. Again, I have the number of rows, number of columns, number of non-zeros, but this time I have row pointers, column indices, and values. Okay, so several indices, I have an array for the row pointers. The size of that array is going to be the number of rows plus 1 instead of the number of non-zeros. And now when I launch my kernel, if you go and look at where I'm launching this kernel, here, when I decide on the number of blocks, it's based on the number of rows in the matrix as opposed to the number of non-zeros in the matrix. Great. So let's implement the kernel. So first, we're going to start by assigning every thread to a row. Every thread to a row. We're going to unsigned int row is equal to blockindex.x times blockdim.x plus threadindex.x. We need to have a boundary check. So if the row is less than CSR matrix dot rows. Okay, what do we do now? Every thread knows that the row it's responsible for. What does that thread do? It needs to find where its row starts and ends. So it iterates from where the row starts until where the row ends. How does it know where the row starts, where the row ends? From the row pointers. So we're going to iterate. We're going to do for unsigned int I is equal to CSR matrix dot row pointers of row, and then we keep iterating until we get to CSR matrix dot row pointers of row plus 1 and plus I. Okay, so I'm going to iterate over the non-zeros in my row. Question? So somebody's asking, should we check if the CSR matrix is less than num rows minus 1? No, because remember, we want to process the last row, but the CSR matrix row pointers itself, its size is going to be num rows plus 1, right? So that's why this row plus 1 is not going to go out of bounds, okay? Because the row pointers array, its size is num rows plus 1, where the very last element, it contains the total size of the array. In other words, that's where the last row is. Okay. All right, so now what we want to do is we want to go and get for every thread, we want to go and get the column index and the non-zero element for that the value for that non-zero. So that's easy. We can do unsigned int column is equal to CSR matrix dot column indices of I, float value is equal to CSR matrix dot values of I. And now what I want to do is I want to multiply the value by the corresponding input value. Let me get the input value. So I'm going to write float input value is going to be input vector of column, right? So I use the column index to go and get the corresponding input value, from here. Okay, and now I want to take that input value and I want to multiply it with val, and I want to do what? I want to add it to the output vector. Now I don't want to read and write the output vector every iteration, so instead I'm going to initialize a count, an accumulator. Let me call that sum and initialize it to 0. And then here I just do sum plus equals val times inval. Okay, and then at the end I'm going to write the value out to the output vector. Where in the output vector? Row, exactly. So out vector of row is equal to sum. So somebody's asking, can we move the reading of the column outside the loop? No, we can't, because this depends on the index, right? Visually, the loop is iterating over the non-zero elements in the row, and each one is going to have a different column value, right? So it's not loop invariant. Okay, clear? Questions? Yes. Somebody's asking if the loop gets unrolled. What do you think? Can this loop be unrolled? So can this loop be fully unrolled? So for a loop to be fully unrolled, what do I need? I need the loop bounds have to be constant. Are the loop bounds constant here? No. So we can't. The compiler can't fully unroll this loop. Okay. All right. Okay. So this is our implementation. We can compile, and we can run, but I think the system is too busy. I'll give it a try to see if we're lucky, but chances are it's not going to finish. Okay. Great. So now we've seen how to implement how to implement SPMV using CSR. Let's go through now our different design considerations. The first one is space efficiency. Let's compare to COO. So compared to COO, how is the space efficiency for CSR? It's better, right? Because instead of having 3z, I have 2z plus n plus 1. So where n is the number of elements, right? Now, if the number of n is much less than z, that can be a significant improvement, right? Almost a 30% better compression. Okay, so in terms of space efficiency, CSR is better than COO. Okay, what's the next consideration? Modifiability. Is it easy to add elements to the CSR? No, it's very hard to add elements, right? Because if I want to add elements to CSR, I have to go back and I have to shift all of the other elements to be able, because I have to add the element to a specific row. So I have to go and shift all the other elements. So modifiability for CSR is very bad. Okay. What about accessibility? What does CSR make easy to access? What does it make difficult to access? So given the row, it's very easy to find the elements in that row. That CSR makes that easy. Given a column, is it easy to find elements in a column? No. given a specific non-zero value, is it easy to find the row and column of that non-zero? So no, right? So given an element, it's easy to find its column index, but it's not easy to find the row index. It's easy for me to go from the row index to the non-zero, but it's hard for me to go from the non-zero to back to the row index. I would have to do a binary search inside of this row pointers array. So here, if I want to parallelize across non-zeros, if I want to assign a thread to every non-zero and have that thread do something for that non-zero, CSR is not a very good representation for that. Okay? Okay. So what's next after accessibility? Memory coalescing, memory access pattern. So let's talk about the three different matrices. Okay, access to the sparse matrix. Is it good? No, it's not coalesced, right? The access to the sparse matrix is very bad. It's not coalesced. What about access to the input vector? Also not coalesced, scattered. Different threads will be accessing have different column values, accessing columns in different time. What about access to the output vector? It's very good, right? No atomics, and the writes are going to be coalesced, right? Adjacent threads will be writing to adjacent elements in the output vector. So CSR optimizes the memory access for the output vector at the expense of the memory access for the input matrix. Okay. What about the last one, which is load balance? Load balance is very bad here because adjacent threads are processing a different amounts of adjacent threads are doing different work, right? And if I have some of these matrices tend to have a situation where you have some rows are much longer than others. You have certain rows that are very, very long. If I have a situation like that, then one thread that has a very long row will hold all the other threads in the warp hostage, and they will have to wait for it to finish processing that row. Okay, so to recap, this is the code that we wrote, and the trade-offs compared to COO are: it has better space efficiency. Given a row, it's easy to find the non-zeros, and access to the output vector are coalesced, and they do not require atomics. But the disadvantages are it's hard to modify. Given non-zero, hard to find the row. Given a column, hard to find the non-zeros in the column. And SPMVs and the memory accesses to the input matrix as well as the input vector are not coalesced, and we have control divergence. Okay, so we saw that now here we had to kind of make a trade-off between atomic operations or memory access pattern and control divergence. Okay, the question is, can we get the best of both worlds? Can we somehow design a format that prevents us from having to do atomic operations, so every thread is responsible for a row, but at the same time arrange the elements in a way where the accesses will be coalesced and I won't have a lot of control divergence?
Can we make it in column-wise order?
So somebody in person is answering, and then I'll come back to the people online. Okay, so just wait a little bit, and I'll repeat what they said. Yes, keep going. Okay, so you're saying we can have some kind of 2D array, and we store the non-zeros for that elements in 2D array, but somehow we store the elements that, like the first non-zero of each row next to each other, the second non-zero next to each other. Is that what you're saying? But that's kind of what CSR did, right? How is it different from what CSR did? Basically, it's more. Okay, let me go to person online. What do you think of it? Okay, online. Somebody want to say something? Okay, I think maybe you changed your mind. So the key idea is that we want to be able to still group not the non-zeros by row, in order for us to avoid the atomic operations. But somehow we want, when every thread goes to access the first non-zero in its row, for those non-zeros to be next to each other. So instead of storing in memory the non-zeros contiguously, we kind of do the first non-zero of all the rows, then the second non-zero of all the rows, and the third non-zero of all the rows, etc. Okay, and there are formats that help us do that. And then we can also do some sorting in order for us to make sure that adjacent threads process rows that are similar in size. So both of these things we will look at next time. So next time we're going to look at how we can solve the load imbalance problem and how we can solve the memory coalescing problem to improve performance. But we're not, the class is not over yet because I still want to do one more format. So I'm going to do one more format, which is the compressed sparse column format, just because it's very related to the compressed sparse row. And as a disclaimer, this format is not a good format for SPMV. This one will actually give us the worst of both worlds, not the best of both worlds. Okay. But I'm doing this format for completeness because I want you to learn about this format. Okay. And then next time we're going to look at the ELL and the JDS formats, which help us get the best of both worlds between COO and CSR. But let's look at CSC. So what do you think the compressed sparse column format does? It's going to same as CSR, but instead of grouping non-zeros by row, it's going to group non-zeros by column. Okay, so here this is the same matrix. I'm going to store the non-zeros in the same column adjacently. So here I'm going to have this values array. It's going to have elements that are in the same column are going to be stored adjacent to each other. Here 7, 2 are in the same column, will be stored adjacent to each other. And then for each one of these elements, I'm going to have the row corresponding row index. And then I'm going to have a column pointers array that tells me where the non-zeros of each column are pointing. So here 0 tells me that the non-zeros of the first column start at 0. 2 tells me that the non-zeros of the second column start at index 2. 4 tells me the non-zeros of the third column start at index 4, etc. Okay, so this is the compressed sparse column format. Any questions about the format? Okay, so now let's look at how can we parallelize SPMV using the compressed sparse column format. Any ideas? Every thread is going to take a column and is going to iterate through the non-zeros of that column and is going to contribute the impact of the non-zeros of that column to the output array. Okay, so but what do we know about the non-zeros of the same column? They're going to be accessing the same input vector element, right? The same input vector element. Okay, so here every thread is going to start at the first non-zero of the column, right? Here every thread is at the first non-zero of the column, and they're going to iterate. So then they're going to move on to the second non-zero of the column, contribute their value, and they'll keep iterating until they've consumed the entire column. And of course, we have to use atomic operations on the output vector. So let's implement this, and then we'll talk about pros and cons. Okay, so I'm going to switch. So I'm going to switch now to CSC. And I'm going to open the kernel. So here now I have a kernel that takes a CSC matrix. If we look at the representation, I have the column pointers instead of the row pointers, and then I have the row indices and the values. And if you look at how I'm launching this kernel, here the number of blocks is based on the number of columns in the matrix. Okay, so I start by assigning a thread to every column. So I'm going to unsigned int column is equal to blockindex.x times blockdim.x plus threadindex.x. I do a boundary check. So if column is less than what? Dot number of columns, exactly. So now that I made sure I'm within bounds, now every thread is going to have to iterate through the non-zeros inside of its column. How does it know where to find them? I start from column pointers of column until column pointers of column plus 1. Right? So I do for I equals CSC matrix dot column pointers of column I is less than CSC matrix dot column pointers of column plus 1 plus plus I. Okay, so now every thread is iterating through the non-zeros. For each non-zero, the thread is going to go and get the corresponding row index and value. Okay, so here we're going to write unsigned int row is equal to CSC matrix dot column indices of I. Float, the value is going to be the CSC matrix dot values of I. Huh? Oh, yes, thank you. Okay, and now what the thread, now that the thread knows the non-zero, it knows its row, it knows its column, what it needs to do is it needs to go get the corresponding input value and then multiply it and do an atomic update to the output value. So let's get the input value. It's in vector of column. Okay, and as you are observing, the input value is loop invariant, right? It doesn't depend on the loop. So I can actually put this, load the input value once outside, then rather than having to load it multiple times. Okay, and now I have to do an atomic update on the output vector at the row index. So I'm going to do CUDA. First, I'm going to get an atomic ref on the output vector. So the type is float, and the scope is the whole device. I'm going to call it outref, and it's on the out vector at what index? The row index, exactly. Okay, and then I'm going to do a fetch and add. So outref dot fetch and add. What do I fetch? What do I add? The value times the input value, right? And what are the ordering semantics? Relaxed, exactly. Okay. Somebody has a question? Somebody's asking, can we forcefully unroll the loop? So you can partially unroll the loop. You can ask the compiler to do a partial unrolling. The problem is that the loop iterations could be as small as 0. So the compiler will have to have an if statement for every loop iteration to check if it's within the bounds or not. So unrolling is it's going to be harder for it to do instruction scheduling between loop iterations. So the unrolling is probably not going to have too much of a benefit. Okay. All right. So let's compile this. Make sure it compiles, but it's unlikely that it'll run. Unfortunately, the system's busy today. What's the? Oh, I called it inval, and down here I called it invalue. So let's just call it inval. Okay, at least we know it compiles. That doesn't mean it's correct, but we're kind of not in luck today. But anyways, what do you expect? Is it going to be faster or slower than the others? It's going to be much slower, right? It's going to be much slower. So let's talk about the advantages and disadvantages here. So compared to COO and CSR, space efficiency, better than COO, same as CSR. Okay, modifiability. It's like CSR. It's hard to add elements to the. It's just like CSR. It's very hard to add elements because that requires you to go and shift all the other elements. So COO still wins on modifiability. CSR and CSC are both just as bad. Accessibility. Right. So given a column, easy to find all the non-zeros in that column. Given a row, it's not easy to find the non-zeros in that row. Given a non-zero, it's hard to find what column that non-zero belongs to. Okay. What about memory accesses? So let's split across the 3 different memory structures. Accesses to the matrix. They're bad. They're not coalesced. Accesses to the output vector. They're not coalesced. Not only are they not coalesced, we have atomic operations on the output vector. So access to the matrix are bad, access to the output vector are bad. What about the input vector? The access to the input vector are coalesced. So as you can see, the COO optimized the accesses to the input matrix, CSR optimized the accesses to the output vector, and CSC optimized the accesses to the input vector. Okay, so the different formats favor different memory structures in this case when we access them. What about load balance? It's just like CSR, we have load imbalance because we could have different columns having a different number of non-zeros. So like I said, CSC is usually not a good format because we got both the atomic operations and the load imbalance and poor coalescing to the input matrix. So CSC is usually not a good format for SPMV, but it is a good format for other kinds of computations. Like for example, if you're doing sparse vector multiplication, CSC could be a good option in that situation. Okay. So this is the code that we wrote, and to recap on the trade-offs, the advantages are we have the same good space efficiency like CSR, accessibility. Given a column, we can easily find all the non-zeros, and we have coalesced memory accesses on the input vector. But the disadvantages are it's hard to modify the elements. Sorry, it's hard to add new elements. Given a non-zero, it's hard to find the row, and given a row, it's hard to find the non-zeros. And then the memory accesses to the input matrix are not coalesced. The memory accesses to the output vector require atomic operations, and the control divergence is poor. So like I said, CSC is typically not used for SPMV, but it is useful for other computations, such as if we have the input vector is very sparse, so we only want to process specific output rows. We don't want to process all of them. And in general, if we have a computation that requires a column-wide traversal, CSC is a good option. For example, if we're doing a vector matrix multiplication instead of a matrix vector multiplication, then we would use, for vector matrix multiplication, we would use CSC, not CSR. Okay? So like I said, we left off saying that we had one format COO that gave us good coalescing and control divergence, but we have atomics. We had another format CSR that had atomic, that got rid of the atomics, but unfortunately we had bad memory coalescing and bad load imbalance. So next time we're going to look at if we can try and get the best of both worlds and have some kind of format that helps us not have atomics and at the same time mitigate the memory access pattern, have memory coalescing, and then also mitigate the control divergence. And we'll talk about that next time. Okay? You're welcome. Bye, everyone.